Hi, good evening. My name is Amizuddin, and I'll be presenting our group research on the American Express default prediction found in Kaggle. Some competition description. The goal is to predict whether a customer will default on their credit card payments in the future. For some context, Amex wants a better machine learning model to manage risk for deciding who gets approved and how credits to offer. So, what will be the impact? Better model will mean more customers get approved fairly, fewer defaults for Amex, which translate to better business, and finally, this is a real world machine learning problem at industrial scale. Before we move on, we would like to acknowledge the contribution by a Kaggle user by the name of Radar for providing the optimized data set. Basically, this data set is a downcasting data types from a floating integer to integer data types. This would translate to less memory. And on top of that, the Parquet format also offers a better compression and faster analytical queries. So moving to the challenges first. So first, the challenges that we face during doing this research is that the huge data volume followed by the memory constraint. Given that the data set compromises of over 5.5 million rows and 190 features, and the limitation of our 16 gigabit RAM requires memory optimization and chunk-based processing to handle the data. Second, the severe class imbalance. So given that the 5% default rate, it is necessary to actually do a class balancing to prevent models from overfitting to the majority class. Third, the feature anonymization. The lack of the domain knowledge due to the anonymization features requires a data-driven techniques for effective feature engineering. And finally, the sequential nature of the data. So the monthly temporal structure of the customer behavior data require temporal aggregation and sequential modeling to capture the evolutionary trends. So, and bird's eye view of our solution. So our final solution is utilizing ensemble learning technique called stacking, right? And at the same time also, we make use of the high performance data processing, such as the Polar data frame for feature engineering. And as for the fast and GPU accelerated model training, we use SGBoost and like GBM. So how do we fare given our solution? We were actually placed at the top 50% based on our solution. So a bit in depth on how we actually perform this prediction. First, we actually perform a data preparation. So using Polars, we actually load this five, over 5.5 million rows and 190 feature of training data sets. What we do next is basically we sort this data with respect to the customer ID and the dates. So S underscore 2 is basically the dates. So as for the feature engineering, knowing given that we have no knowledge of the features, the best we could do is actually to deal them in a numerical or categorical data. So as for numerical, what we compute is that we compute for the mean, the standard deviation. Why we do that? Because we want to capture the central tendency and volatility. Second, we will catch the minimum and the maximum to flag the extreme events. And finally, we capture also the last of the customer most recent status. And as for categorical data, we compute the last observed state followed by the number of counts, which indicates the diversity of their categorical history. Here, next, we'll be discussing more on the standard workflow. So, using the train data set and the train labels, we merge them into one data, right? Go through this feature engineering, and once the feature engineering is done, we feed it into the k-fold iteration. Each k-fold will produce a prediction, which eventually become a meta feature. At the end of this k-fold, the meta feature will then be merged into one single data set and fed into the logistic regression model. and that will produce a final prediction. As for the model training, there are two different models used in the K-folds. First will be the SG Boost, second will be the Light GBM. Something to note is that the training is done at a maximum of 4,000 rounds and especially evaluate the watch list on the training sets. So if there is no improvement over 300 consecutive boosting rounds, the training will stop early. So some experimental study, the initial approach was to use a single model prediction and to know how fair we were do well was to actually perform based on the leader, leaderboard score. Um, Using this benchmark, we will manually tune the model hyperparameter to improve the prediction. However, this approach has its limits on how well the prediction produced. So the next approach was to improve the feature engineering. However, this have a dependency to the hardware capabilities. Why is this so? Is because the more feature added, the more memory required. So finally, we decided on using ensemble learning technique based on the same feature engineering techniques that we used earlier and the same model hyperparameter that we researched earlier, and we notice there is an increase in the leaderboard score from 0.79551 to 79699. So to put it in context, we will initially place top 60% using the single model approach. But the moment we start using the ensemble learning approach, we will place in the top 50. Okay, as for the lesson learned during this project was that first, the necessity of robust feature engineering. So basically, for a successful time series classification relies on aggregating customers' history to capture the statistical trends and the most recent status, thus dramatically boosting the predictive power before model training. Second, leveraging on accelerated computing for training speeds. So the strategic use of parameters like device equals to CUDA and tree method equals to history in SGBoost is essential for high velocity projects, enabling rapid training and iteration on massive data sets. Third, the risk of optimistic performance estimates. So by evaluating the model solely on the training data results in an inflated performance metric. A rigorous validation technique like K-fold is necessary to achieve an unbiased performance estimates. And finally, workflow simplicity versus production readiness. So while convenient for rapid prototyping, in what we do in our Jupyter notebook, for immediate submission as well, right? But avoiding the model saving step is not actually scalable. This requires explicit model serialization for production deployment or sharing. And that's about it. Thank you for your time and hear from you more again. Thank you.